In this video, I'm going to introduce you to the scalar product, also known as the dot product. And this is the result when we multiply two vectors together. And the result we get from this is a scalar. And remember, a scalar quantity has size or magnitude only. It's not got direction. So first we're going to have a look at the scalar product from component form. So let's say we have two vectors in component form, vector A, and it has its I and j components labelled A1 and A2, and vector B with components B1 and B2. So to perform the scalar product of vector A times vector B, we simply take the I components from each vector and multiply them together, and then we add on the multiplication of the j components. So let's see that in action. So we've got vector u, v and w as outlined in component form. First of all, we want to find the multiplication of vector u times vector v. So that means we're going to have 3, 5 multiplied by 6, negative 2. So I'm going to take the I component from each one and multiply it to get 18, and then I'm going to take the j component from each vector and add that on, and I'm going to get negative 10. So 18 take 10 gives us a scalar quantity of 8 when we multiply these two vectors together. In our second example, we've got vector u multiplied by the result when we add v and w together. So remembering when we add vectors together, we simply add the I components and the j components. So for vectors v and w, it's going to be 6 and negative 3 that we're going to add together, and negative 2 and 4. So we're going to multiply vector u by the result here, which is 3, 2. So again, we're going to multiply the I components to get 9. We're going to add on multiplying the j components, and we get 10, and we get a scalar result of 19. If we have, as in part C and D, involving a coefficient multiplied onto, or a scalar multiplied onto the vector, we can treat it in a couple of ways. We can treat it as we would normally when we're multiplying. We want two lots of vector u, so two lots of 3, 5, times negative 3 lots of negative 3, 4 for vector w. So we can just multiply those into the vector. So we'd have 6, 10 multiplied by 9, negative 12. And then we could do our scalar product, multiplying the I components together. So 6 9s are 54, and adding on the j components of negative 120, and we get negative 66. What we can also do in this example is multiply the 2 and the 3, negative 3 together first. So we'd get negative 6 lots of u times w, and then we'd have negative 6 lots of the scalar result of multiplying those I and j components together, which will give us negative 6 lots of 11, which will give us still negative 66. So we get the same solution. So with part D, we've got the subtraction of two vectors multiplied by 2w minus u. So again, we go about this as we normally would. When we subtract two vectors, u minus v will give us negative 3, and 5 take negative 2 is 7. Multiplied by two lots of w take u. So we've got negative 6 take 3, which will be negative 9, and 8 take 5, which will give us 3. And now we can perform the scalar product. So I'm going to multiply the I components. Negative 3 times 9 is 27, plus 3 times 7 is 21, and we get a scalar result of 48. In question 2, we can see we've got two vectors, vector u and vector v, but we want to find x if the scalar multiple, the scalar product of these two vectors is negative 20. So we're just doing the inverse here. We know the scalar result, but we don't know the j component in vector u. But we know that negative 20 was the result when we multiplied 5x to 6, 3. So negative 20 is going to equal 30 plus 3x. So we can go ahead and use our skills to find out that x is negative 50 on 3, or negative 16 2/3. Now we're going to have a look at another format for the scalar product. And this is when we know the magnitudes of two vectors and the angle between them. So if we've got these two vectors, whether in component form or with their magnitude and an angle, we can perform the scalar product. And this is by saying that the scalar product is equivalent to the magnitude of A times the magnitude of B times the cos of the angle between A and B. A really important note here is the angle between two vectors is when they're both moving away from a point, so this would be the angle, or when they're both moving towards a point. So be really, really careful about that. We'll see that in play in a moment. Just some extra notes. If the scalar product is above 0, then theta is acute, and if the scalar product is below 0, then theta is obtuse. So when we think about this, if we have two vectors A and B and they're perpendicular to each other, so suggest that we've got vector A in this direction and vector B perpendicular, means the angle between them is 90 degrees. So what would the value of the scalar product between them be? So if we think about this, we would say, well, the scalar product would be the magnitude of A times the magnitude of B, and we would have two values there, times the cos of 90 degrees. But using our knowledge, cos of 90 degrees equals 0, which means we're going to have a number multiplied by a number multiplied by 0. Therefore, the scalar product between these two vectors is equivalent to 0. So when they are perpendicular, the scalar product value is 0. That's a really nice point to keep handy. So let's see this format of the scalar product in action. With A and B as defined in the diagram shown, determine the scalar product of A and B. Well, I can clearly see that I've got the magnitude for each one and I've got an angle. So I'm going to use the magnitude of A times the magnitude of B times the cos of the angle. So I've got A as 6 units times B is 4 units times the cos of the angle between them. But what I notice is they're not both moving away from this point. So I need to redraw so that A and B are moving away from the point. Essentially, it's just moving B onwards. And so the angle between them is in fact 60 degrees. So I would like the cos of 60. So I've got 6 fours are 24 and the cos of 60 is a half. So the scalar result is 12. In our final example, I'm asking you to find a vector which has a magnitude of 10 and is perpendicular to 3, 4. So I'm going to call the vector I don't know A, because I know its magnitude is 10. And I'm going to call the vector that it's perpendicular to 3, 4. What I know about this vector A, if its magnitude is 10, I don't know its component form, so I'm going to call it xy, which allows me to define its magnitude as x squared plus y squared equals 100. When I know that it's perpendicular to another vector, I know that if I do the scalar product of vector A times vector B, I'm going to get a value of 0. So if I carry out this scalar product on the left, I'm going to get 3x with the I components plus 4y equaling 0. What I've got now is two equations with the two unknowns, x, y, to find that vector in component form. So I could rearrange this equation here and then substitute it into the first equation I made, or I could use solve mode on my calculator, and I get x equaling negative 8 and y equaling 6, or x equaling 8 and y equaling negative 6. So therefore, I can define the vector that it has a magnitude of 10 and perpendicular to 3, 4 as either negative 8, 6 or 8, negative 6. What I'd like you to do now is have a look at the following 4 questions on your worksheet and pause the video and have a go at them using these 2 forms of using the scalar product, and then come back to the video and you will see the solutions to check your answers before we progress with the scalar product in class together. So our solutions to question 1 are just some simple use of the scalar product, multiplying the I components and adding on the j components. We get 14 and 15 as our scalar results. In question 2, we're asked to find the angle between the 2 vectors. That's asking to find theta. We know what the scalar product is worth, which is 27. We also know the magnitude of the 2 vectors I've called A and B, and therefore we can find the angle at 6.34 degrees. In question 3, we can find x, the unknown I component in vector B, if we know that they are equal, their scalar product is 0, which means they're perpendicular to each other. So x is 7.5. And in our final question, we have the magnitude of a vector and the angle that is between them. And that's because if we have one vector and we're inclining 30 degrees, it means both vectors are moving away from that point. So our theta is 30 degrees. And we can form the 2 equations to show the magnitude of vector A and the scalar product, what it should equal. And that gives us vectors 15.8, negative 20.7, or 25.8, 3.3.